Hello and welcome. Today we're going to talk about an example of using Taylor's inequality to determine the truncation to achieve an error criterion. Okay, so let's set up the problem. The idea here is we're given an f of x. We're also given some domain. Okay, where d is some positive number, okay? And then we're also given an error tolerance or criterion. So in this case, we're going to call it epsilon, right here. And the idea is find a Taylor polynomial degree n that we determine that n so that the polynomial, which we'll call Tn of x, that's the polynomial, minus f of x in absolute value, and this is what we call the error, is less than epsilon. Okay, so the goal here is to find a smallest n to achieve this. All right, we're going to do a specific example of this. All right, so let's talk about what we're given. We're given f of x is equal to e to the x, right? And we know that the Taylor polynomial can be written as such. Okay. All right, and then the truncation, of course, now just stops at a specific value of n. Starts at 0 and goes up like that as follows, right? All right, and so the domain we're going to be interested in is going to be x from negative 1 to 1, all right? So that means our expansion point is just going to be 0, all right? And we're going to use that Taylor inequality. All right, so we know that f minus Tn in absolute value is less than or equal to m over n plus 1 quantity factorial times x in absolute value to the n plus 1 power. Okay. All right, so what we have to figure out, of course, is what is m. We know that m is going to be the maximum of the absolute value of the n plus 1th derivative on that interval. Okay, in this particular case, we know the derivative of e to the x, all the derivatives are just e to the x. And we know the interval is negative 1 to 1. So it should be very evident that the maximum value is going to be if we plug in x is equal to 1 in there, and we get e to the 1 in absolute value, which is just e to the 1, or otherwise known as just e. All right, cool. All right. So now our error tolerance. Okay, what we want to do, I want epsilon to be equal to 1/20th, i.e., I want to find out what value of n gets me this. Less than 1/20th. All right, let's see if we can figure this one out. We know the top value here. So what we want to do, of course, is actually make f minus Tn. We know that it's less than or equal to e to the 1 over n plus 1 quantity factorial times x to the absolute value n plus 1, we want that whole thing to be less than 1/20th. So what we're going to do is we're going to put this in between right there. So once I find this end that does this, then I'm set. Okay, I think from here we'll just give ourselves a little bit more space, and we should be able to sort this one out easy enough. Now we know that E is about 2.71, so it's of course less than 3, more than 2, and that should come in handy. The other thing we know is that x is on the domain -1 to 1. So if I look at this inequality, I can write it like this. I want to make this as big as possible. So the idea here, what I wrote down here just a second, is we want to make it as big as possible in x. We want it to cover every single x value that is possible, and we want to make that as large as possible, and then find an n that then subsequently makes it smaller than 1/20th. All right, so clearly what I'm going to do here is plug in x equals 1. So what we have is e to the 1 over n plus 1 factorial times 1. We want that to be less than 1/20th. All right, so this is the thing we got to solve, and once we figure out how to make this inequality true, we get what we want for free, that the error is small. Okay, this should be pretty straightforward. We can start with n is equal to 1. That means it's 2 factorial, and of course we have e over 2. Well, that is bigger than 1/20th, so no, that won't work. N equals 2. Well, that will give us, that means that 2 plus 1 factorial is equal to 3 factorial, which is 6. So that means e over 6, well, that's still bigger than 1/20th. That's not going to work. N is equal to 3. That gives us a 4 factorial. Which is 4 times 3 times 2, which is equal to 24. So of course we have e over 24, which is still just a little bit bigger than 120, or 1 over a 20th, about 3 times as big, about. So that's not going to do it, but I bet n equals 4 is going to do it. N equals 4. That's going to be equal, that'll give a 5 factorial, which is going to give us e over 120. And remember that e is slightly smaller than 3, and that 3, well, I can multiply it by this. That'll be 30. Hold on. What's the best way to factor 120? Well, of course, 120 can factor many, many ways. But I think what we want to do is have, what we want to do is make it 30 times, oh, no, that's not what we want to do. How about we do 3 times 40? The 3's cancel, and we're left with 1/40th, which is in fact less than 120. So that's what does it. So it's an n equals 4 is the correct answer in order to ensure the accuracy that we want. All right, so that's how you do the analysis. You're essentially enchaining together several inequalities. You know this one is always true, but we just need to make this small enough so that it's smaller than 1 over 20. So we just had to figure out which value gave it to us. All right, now I want to just give a graphical depiction of the kind of thing that's going on here. So in general, in general, Taylor's inequality does something like the following. If you have some sort of function, f of x, right? And then you have some expansion point, call that a, then you know that you're going to have some sort of, this is going to be Tn of x, right? And the idea is if you look at the error, so all the spots where the error is basically where the functions differ, like that. And if I go within a certain region, so this is a, and that's negative, this is a minus d, and that is a plus d. What we want to do is make that error as small as possible, right? So the max error here, so what Taylor's inequality does is it basically says that it gives a bound for how large error can be between Tn and f on a domain. Okay, so that's just the general principle behind this. Well, I hope this video clarifies how to do an analysis like this. These sorts of things are very important because, of course, scientists and engineers need to specify accuracy in order to ensure correct function. Whatever scientific achievement or whatever goal they want to have with whatever they're doing, a lot of times there is some pre-specified level of accuracy that's desired, yet in many times the function itself is either not known or maybe it's only partially known, and you have to take some sort of approximation of it, and you're going to use a Taylor series in order to do that. And because of that, we have these issues. Anyway, I hope this video clears up how you can use Taylor inequality. It is one of the most important theorems in calculus. I would call it one of the fundamental theorems, even though they don't really call it that, but I certainly do consider it one of the most important theorems. All right, thank you very much.